Hey guys, Amol here. So I just wanted to give you a brief update on something that I'm working on. It's a new language that I'm trying to build, and I have not done this before. Um, but recently, what has happened is there are some things that I was working on at my day job, and also I was helping out a friend with a similar thing where I had to parse different kind of text input and make meaning out of it, right? These were like more structured, formatted on the data that I was working with. It was not natural languages or anything like that, so I couldn't have gone towards a more NLP oriented approach. Um, so I was tasked with writing some type of parsers, and then the parser should dynamic, so it should handle different type of stuff, different type of input, right? So how this kind of inspired me to do a little more research on how different types of parsers work, how languages are built, how interpreters are built, even, right? And then this pushed me more and more in the direction of actually doing more research on how computer programming languages are built, right? So, so what I have set out to do right now is I'm thinking I'll create a Python like language. I'll try at least. We'll see how far I can go. Whatever happens, I'll share with you guys, and then all the source code will be on GitHub, and you can check that out. So I'm trying to build like a Python like language because I really love Python. I think it's really productive. It's easy to use, but there are certain parts of it that I don't really like, and I think a lot of people have some or the other issues when it comes to Python. So it's not going to be anything serious. I'm just going to build a toy language. We'll see how it grows, right? So uh, and I'm documenting this so you can watch me create a programming language or try at least, right? Um, while I do it, and maybe take inspiration from it. And so all in all, the world of people who write compilers, interpreters, parsers, programming languages. It's a very small world. There are not a lot of resources. There's a not a lot of guides, especially when it comes when you want to do real world stuff. There's no pointers, and then it's a very intricate subject which has a lot of areas and a lot of details and a lot of things where math is included, right? Different uh, subjects like theory of computations is included, right? So I found it very interesting when I dug deeper. I have no idea how to do it and what to do and what not. And then especially it's like I said, it's a niche area of programming where not a lot of people venture into. And so the resources are also they are hard to come by. Now, before I move on to the actual code, I wanted to give you an introduction on how a typical programming language goes from the source code to actually running on the machine on the CPU, right? So the first stage is obviously you write some source code, and that source code is defined and saved in a file, right? That is your source input, right? This source input is passed through the multiple stages, and the first stage is what we call a lexical analysis stage. So lexing or uh, and the system that does it's called a lexer or tokenizer. So what it does is it takes a string input, right, a big chunk of text, and basically starts identifying different parts of it as maybe an identifier, a literal, right? Maybe some symbol, like a reserved keyword. So it tokenizes the big chunk of text into small bits, which are called tokens, right? This whole source code gets divided into different parts. So, for example, here this active will be one token, X and Y will be other two tokens, def, which is a keyword. This is also will be converted into a token. Right? So this tokenizer then gives us a stream of tokens. It maps them properly with a given grammar. Now grammar is just a set of rules, and when it comes to tokenizer, you'll see later how the grammar for a tokenizer is coded. It's basically a bunch of regex expressions uh, that extract parts of the source code and convert it to different tokens. Token can be just a simple class or a struct even maybe in a programming language, right? So after this stage, we move on and we have a token of stream. We have a token stream that is coming. All right, and these tokens are then passed into a parser. So parser's job is basically to take these streams of token and apply another set of grammar rules, uh, which basically and basically create a abstract syntax tree out of it. So this abstract syntax tree or AST is a data structure which arranges the the stream of tokens that we are getting here into a uh, into a into a format that can be compiled down further, right? So basically, the output of parser is an abstract syntax tree. I couldn't draw it here, but it's you can think of it as like a normal tree data structure with different nodes as tokens, right? So maybe here in our example, will have X and we'll have Y as two leaves, and this plus operator, right? The operation that we are doing, that will be the root node of this subtree, right? So and then there will be more collections out of these. So after the passing stage, we have our AST. That AST can now then be compiled, uh, and then there's a compiler, or generally there's either a compiler or there's an interpreter setting after the AST stage. So the compiler says, okay, I have these nodes. I see a for loop is running in this tree. Can I maybe optimize it? So it does a lot of optimizations. It does a lot of code translation, and it basically translates your source AST into uh, machine or even a lower level language. Some compilers translate source code into C. It may also translate it to Java. It may translate to LLVM, intermediate representation, right? So there are a lot of targets. So once you have the uh, machine code or the optimized bytecode assembly code or a binary, right? You can simply go ahead and run it in your runtime. So runtime is another piece of software which basically keeps pools of all the variables and things of that nature. It also does help. It helps in doing garbage collections, right? In garbage collected languages. And runtime is where your program will run. So it's like the environment for your program. So for Java, the runtime is the JVM. It's the Java Virtual Machine, right? Which provides everything needed for a Java program to run. So that is what the runtime is. Um, Now, error checking is also a big part. So, let's say the user who's writing our language he has made a couple of syntactical errors, or maybe right, even he has added some semantic errors or logical errors, whatever kind of errors, right? If the compiler needs to check for those errors. So, the error checking mainly happens in the parsing stage and in the compilation stage. So, we also need to check for errors, and we need to report those errors, right? So there's a lot of code dealing with error checking also. For example, let's say user is trying to access a variable which he hasn't defined before, right? So all of those will be caught in these stages, either the parser or the compilation stage, and it's done differently in different languages and different compilers. So that is basically the flow of uh, of a language being compiled from source code down to native machine code or a low level code where it can target and run in the CPU. Let me make it clear. Right? So this is kind of the flow that we have. So let me show you guys what I've done so far. So basically, right now I only have the Lexing or the Lexa stage in place. I don't have anything else. I'm about to start writing parser, but for the Lexer, let me show you how it works in practicality. So this is a very simple source code um, for the new language. It just add function. So basically what you're doing is you're defining an anonymous function which takes two parameters and returns x plus y. You're assigning it to a variable. So that's it. That's all we have right now. And once, uh, so this is our source code. Now we have to do um, a lexical analysis on it and get all the tokens out of it, right? So what I'm using a library called Python LexYak. Right? So LexYak is a very popular and very well documented uh, type of lexer and parser, and I'm using the Python implementation of it. So which is PLY, right? So you can look it up, you will know what it is. So basically, uh, first thing that we have to do to use any type of lexer is you have to define your grammar. In terms, when it comes to lexers, the grammar basically means, okay, uh, uh, what are we trying to pass, right? What these tokens mean. So here, this is the file where I have defined all my grammar, and I'll walk you through it one by one. So to start with, we simply have an object which defines all our reserved keywords, right? So for example, and or if for right these sort of things. Now we have a set of tokens also, right? So we are saying there will be a token called ID, there will be a token called plus, there will be a token called minus, and so forth. And you can see what these represent exactly in the comments on the right. Now we are telling the compiler, telling the Lexer uh, how to capture these tokens. So to capture a plus, basically it has to apply a regex, which is this, right? So, and it's a very simple regex. It's just a plus symbol with an escape, right? Um, so we have defined all the regexes for all our tokens, right? So and then we have some other. So for a little more complicated type of tokens, for example, identifier. So identifier is like a word, right? Maybe you know what a name of a function, name of a variable, name of a class. These are identifiers. So how do we capture those? So basically, we have a regex which defines that identifier can either have A to Z, it can have underscore scores, and it can have 0 to 9 at the end, not towards the beginning. So that's all the regex says. And then we are doing some co we are doing one line of Python to basically figure out whether the token that we have identified is it a reserved keyword, right? If it's a reserved keyword, then we change the type of the token that we get. That's all it's happening. And then we have few data types defined, so ints and floats. We have left parentheses, right parentheses, and then we are storing some metadata in our Lexer also. So we are increasing the parent count, and then we are decreasing the parent count, right? So and a lot of it is You can get probably this code from the directly from the documentation from of PLY, right? I haven't written the full file. It's from other sources. Then what we have is we have an indent lexer because the language that we are trying to build, the language that we are trying to build, it's an indented language. So we will not be using curly brackets or anything like that to identify the blocks in our code. We'll be using indentation. So we also have a indentlexer.py. This file basically contains an indentlexer which basically does a second pass after the first part to identify different indentation and dedentations, right? So and then we have the final lexer py file, which basically creates an indent lexer, passes the actual ply lex object right inside our index lexer, and then we basically it's just some boilerplate to run and test the lexer. If I run it now, Python try. So we see it prints out the stream of lexical tokens, right? So at first, um, let me open the source code on the left side, right? So here you can see we have add at first, and then an equal to sign, and then a keyword, and it has identified all of that. So firstly, it says there's an identifier, then we have a token which is equals, and then we have a token which is type of function, right? So this is why this time it's not saying ID because fn is a reserved keyword, right? It's saying fn. So on the fourth token that we have is again an ID which is x, and this is how basically the whole thing gets tokenized. And in the end, we have a EOF marker, so we know okay, we can stop parsing, we can stop the lexical analysis, right? And then we have a new line. It is also capturing new lines because the new lines are also important, right? Especially in an indentation based language. So this is what we have so far.